Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to explore a new data structure called a queue. Queues are a first-in, first-out data structure. They're used to process data in order. So the first item that arrives is the first item that's processed, and the last item that arrives is the last item that's processed. And this is wholly based on time, when things arrive. Sometimes queues are referred to as lines. So if you're waiting in line for something, you're in a queue. Queues are fundamental to computing. Think of it this way. Whenever the processor is running those commands in a procedural manner, it's running them first in, first out. The first command that is put is the first command that happens. Now, queues have operations that are universal. When you add an element to a queue, this is called enqueuing. When you remove an element from the queue, it's called dequeuing. Now, a little further detail. When you enqueue, you always enqueue at the end of the queue, and when you dequeue, you always remove the first item from the queue. This preserves the first in, first out nature of a queue. Some other operations that are very common for a queue is peek. Peek allows observation of the first element without removing it from the queue. And also, print is very useful just to make sure that our queue is behaving correctly. It's really good for debugging. Now, if we were to implement a queue, there's a couple of different ways that we can do that. We learned before about two foundational data structures, the array and the linked list, and a queue can be implemented in both of those ways. Going into a little more detail, there are two major references, no matter how you implement it, that we have to keep track of with a queue. The first one is the head reference. That is the first element that is in the queue. The last element is the tail reference, so that is the last element in the queue. We use those to enqueue and dequeue because we always enqueue after the tail, and we always dequeue from the head. Now, before we get to implementing the code for writing a queue, we have to take this into consideration. As we just described, a queue can be implemented in multiple different ways. So a queue could be implemented as an array, a queue can be implemented as a linked list. But even further than that, a queue can be implemented as a shifting array, a queue can be implemented as a circular array, a queue can be implemented using a singly linked list, a queue can be implemented using a doubly linked list, a queue can be implemented using a singly circular linked list, a queue can be implemented using a circular doubly singular. It can be implemented in a lot of different ways. But the main idea is that all queues will have the actions enqueue, dequeue, and we're also going to add in peek and print. As one thing can be implemented in multiple different ways, this is the idea of polymorphism. Now, in order to use this, we're going to use this structure called an interface, which basically acts as a set of rules for any class that implements those interfaces. Now, as we have this relationship that this array queue and this linked list queue implements this ensures that every implementation of this interface will have these methods built into them. So this array queue will enqueue and dequeue elements based on an array, and this one will enqueue and dequeue elements based on a linked list. This gives us flexibility. That way we can create one type of queue and have it implemented in multiple different ways. And this really depends on our problem, because the advantages of an array is it's not resizable in memory, so if we know the fixed size of a queue, then maybe it makes more sense to use an array implementation. But if we needed a queue to resize, then maybe a linked list makes more sense. Let's go ahead and start developing some of these queues. Now, going over to the code, the first thing that we're going to do is create that interface. So much like a class, we're going to create a new interface this time, and we're just going to call it the QI, the Q interface. Now, much like a class, this creates a type called QInterface or QI. However, an interface cannot be constructed. A class can be. So in other words, we can't use the word new and create a new instance of this QInterface, but we can construct instances that implement this interface. We'll get to that in a little bit. Now from right here, we want this to be a generic queue. It could be a queue of any type. To do that, we use the angle brackets and place type T, and now this is a queue interface of whatever type. Now, inside of an interface, it doesn't have any functional code. All we have are method definitions. So we're just going to define public void enqueue, passing in T data, or we'll make it A data to stay consistent. dequeue removes the first item and returns. So this is why we have public and we have to return type T, because not only do we remove, but we also return. dequeue, no parameters. We also had a similar method, public T peak, which returns the data that's found in the first item, but doesn't remove it. And also public void print, which just prints out all the items. Now that we have this, let's see how this could be used. I'm going to go ahead and create a tester class. I'm going to include the main method. Now, this QI becomes a type. So what I could do is create a QI, and I'll just call it Q. Now, as this is a generic type, maybe I want to create a queue of type, let's keep it easy and create integers. Now, the thing that I brought up is that interfaces cannot be constructed. They're a non-constructible type. So I can't do this. Q is equal to new QI of type integer. As we can see here, this gives us a syntax errors. Interfaces cannot be constructed, but classes that implement those interfaces can be constructed. I'm going to go ahead and comment this out, and now let's focus on creating a class that implements this queue. The first version that we're going to create is an array queue, and we're going to start out just by doing some of the basic setup. We're going to go ahead and create a new class, and we'll call this the array queue. Now we want this array queue to be generic, so it can be an array of any type. So we're going to use the generic type T here. Now, as this is a queue, we need to have this implement all of the elements that's found in this queue interface. Now, the queue interface is also assumed to be a generic type, so now we pass this T along there as well. So whatever this array queue of this type is, now also passes this type to our interface. Now inside of this class, what we have is a private T array, which we'll just call the queue. Next, we also have a private int head index. So this is the first element in our queue, and also a private int tail index. This is the first null element, or one past the last element. We are making this distinction because this makes the coding a little easier. The tail index does not refer to the last element in this queue. It refers to one element past that. So it is the first null element or one past the last element. If we needed to get the last element in this queue, then we would need to have the tail index -1. Now let's create some constructors. Public array queue. Here's our default constructor. And after that, we're going to do a parameterized constructor. And the parameterized constructor is going to be a little different because we're just going to assume that the only element that you should be able to modify via parameter is the size of the array. Now, as both of these are going to be constructing this new array queue and assigning each one of these values, they're effectively doing the same thing. They're initializing all of these elements. That feels like a different verb, so what I'm going to do is create a private void init, which is short for initialize, and then I'm going to pass in this int size. From here, we're going to go ahead and assign the head index equals the tail index, which is equal to 0. Now from here, we need to evaluate whether or not this size is valid for an array. I'm going to argue that the size needs to be at least size 1. So if size is greater than or equal to 1, then what we can do is construct Q. Now the thing is, we can't just construct this of a new type T. However, what we know is every type that is this type T inherits from object. So what we need to do to make this work is we have to typecast this T array and then construct a new object of this size. Once again, every object type, in other words, everything that is a class in Java, has always inherited from the class object. To do this, we construct this new object array and then cast it as this specific type T here. Now, if that's not true, we should construct this queue based on some sort of default size. A default size is something that doesn't change, and something that doesn't change should be created as a constant. So back inside of my properties, underneath my instance variables, I'm going to create a public static final int default size, and I'm going to set it to 100. So now, inside of initialization, what we can do is set Q is equal to typecast T array new object of this default size. So at least if someone were to put an incorrect size, this array would be constructed either way. Now from our constructors, we call init from our default constructor using the default size, and also init with our parameterized constructor, passing in the parameter size. Now we have the basic setup for this array queue, but you'll notice that there's still a syntax error on our type. The reason being is we have not implemented all of the methods that are defined inside of here. So now we need to implement enqueue, dequeue, peek, and print. We're going to focus on enqueue first, but there's some details we need to go over about how this works. Now keep in mind that the head index is the first element in this array queue. Now the tail index indicates that it is the first null element. This is slightly different from an earlier example. So if we were to look at this example of an array queue, we can see that the first element starts here, and the last element is here. However, the tail index is always one past that last element, so it refers to the first null element right here. This is the start of the queue, and this is the end of the queue. In order to make this as efficient as possible, what we do is we have the head index and the tail index both be movable. But in order to make this work correctly, we need to advance head and tail based on a circular way. The way that you can think about that is if we're moving an index forward in a circular way, if my index was right here and I need to advance it by 1, then it moves to right here to the first index. So if we're at the last index and we advance it in a circular way, we start back at the first index. The way that we do that is we assume that the next index is our current index plus 1, but modded by the array length. Showing this over here, we can see this is an array of size 6. If I'm at index 5 and I do 5 plus 1, which is 6, 6 mod 6, there's no remainder, so it jumps back to 0. By implementing it in this way, we can avoid a shifting operation. So let's assume that the head was always going to be 0. If I'm going to remove this element, then I need to shift everything over by 1. If we have a large queue, like over 1,000 or 1,000,000 elements, and we remove the first item, if we were to shift, then we would have to shift over 999 elements to make that work. However, if we just advance the head and the tail, well, this is just one operation, and this is more efficient. Now, this can also create some weird scenarios, because the thing is, we can have the head index have a larger index value than the tail index. However, the concept is still the same. The start of the queue is right here, and we advance in a circular way until we get to the tail index. Now, applying all of this, when we enqueue into an array queue, the first thing we do is we add the new element to the tail index and then advance the tail index circularly. So, if we were to add the new element to right here, and let's say that it was 4 in this case, we added it to the tail index, the first null reference. After that, we have to update the tail index by increasing it by 1 and modding it by the size. If we increase 5 by 1, 5 plus 1 is 6. The size of this array is size 6. 6 mod 6 is 0, and so it just reassigns the tail index to point to 0, the first null element. Let's see how this works in code. First thing, public void enqueue, TA data. Now, we know that a queue is not resizable in memory, so when we're adding elements to a queue, one of the first checks we need to make is whether or not this queue is full. This becomes a little more complicated because we're not assuming that the head is always at 0. The head and tail can both move. So the way we need to evaluate if this queue array is full is if queue at index head index. This is the first element. If this is not equal to null, that means we don't have an empty queue. And the head index is equal to the tail index. The tail index is always assumed to be the first null element. If the tail index and the head index refer to the same thing and it's not empty, then we have no space left to add something new. If that's the case, we simply return. However, if that's not the case, then we take Q at the tail index, which is our first null element, and have that point to A data. Then we update tail index is equal to tail index plus 1, but now mod q.length. And this will advance the tail in a circular way. Now let's do dequeue, and let's focus on the concept for that. Now when we are dequeuing, we are removing the first element. So the first thing that we need to do is save a reference to the data that's at that head index. Simply enough, we're going to save this value as some sort of return value right here. We then advance the head circularly and return that value. Now you may notice, again, the start of the queue is here, the end of the queue is here, and this is every element in the queue. We technically didn't remove this element, but that doesn't matter, because the head starts here and the tail is right here. everything outside of that is considered to not be in the queue. So eventually, this value may be overwritten. Now let's see how that's implemented inside of code. Public T dequeue. First thing that we're going to do is we're going to set T ret is equal to Q at the head index. This is saving a reference to the data that is in that head reference. Now we advance the head index forward circularly. Head index is equal to head index plus 1 mod q.length. And finally, return ret. And that's all we have to do in order to dequeue something from this array-based queue. Now, if we notice, we still have a syntax error on this type, and that's because we haven't implemented the methods print and peek. Let's go ahead and implement those. Public T peek. All we're going to do is return Q at this head index. Public void print. Now the print method has usually not been an issue, but this time it becomes a little more complicated because what we're assuming is this queue works in a circular fashion given that it's an array. In order to do this, the first thing that we're going to do is system.out.println queue at this head index. After that, we're going to use a for loop. For int I. Now we're not going to start it at 0 because we can't assume that index 0 is the head element. We need to start this at the head index, but as we have already processed it, in other words, after we have printed this, we need to move it ahead by 1 by advancing it by 1. However, if we're advancing something, we need to make sure that this works in a circular fashion as well. So not only do we have to do plus 1, but we also need to mod it by the q.length. So now, we need to keep moving this until we reach that first null element. In other words, until I is equal to the tail index. Or looking at this backwards, while I is not the tail index, then we're going to keep running the body of this loop. Now what we need to do is update this I, but we have to update this in a circular fashion as well. So in this case, we do I is equal to I plus 1, but this time mod q.length. Now inside of here, all we're going to do is system.out.println q at index I. Now let's see if this works. Going back to our tester, we have already declared that we're going to have this new queue that we're simply calling queue. Now let's construct this queue as an array queue. Q is equal to new array queue. Now this works because our array queue implements this queue interface, and so we can substitute this array queue for this queue interface. Using this, let's now experiment with how this is going to work. So for int I is equal to 0, I is less than, let's say 10, I++. Q.enqueue I. Q.print. Testing this out. Sure enough, we have all of the elements being printed out in order first in, first out. Now let's see what happens after some dequeues. int val is equal to q.dq, int val2 is equal to q.dq, then q.print. So as we can see, it starts right here, and it's removed the values 0 and 1 and stored those into the values right here. So now we have this array-based implementation of a queue. Let's now create a linked list implementation of the same thing. We're going to start with some initial setup. Let's go ahead and create a new class, and this one is going to be called the LL queue. Now this linked list queue is going to be generic type T, and also it must implement this queue interface, this QI, also passing the type T. We're going to implement this based on a singly linked list. And as we know, with a singly linked list, we need to group together the information into a structure called a node. So internally, we create a class, private class, list node, where we're combining together T data with list node link. Now we just write a parameterized constructor, public list node, TA data, and list node, a link. And then we just directly assign data to point to a data and link to point to a link. With the linked implementation of these data structures, usually the first step is to create that node that we're going to be using internally. Now, after that we've created that structure, we need to create some specific references. Private list node, head, this always points to the first element, and private list node, tail, this always points to the last element. You may notice that we're not using a current and a previous. The reason being is we don't need them. If we're removing element from this linked list, we only need to refer to the head element. If we're adding elements to the end of the linked list, we only need the tail element. We don't need a current to be able to move around this because we're not adding or removing elements in the middle. It's always happening either at the beginning if we're removing and at the tail if we're adding. Now to create the constructor, private LLQ, and let's just set head to tail to null. Now that we have that, let's explore how we enqueue. Enqueuing in a linked list is fairly straightforward because all we need to do is create a new list node with the data and then have the tail element point to the list node and update the tail reference. So just like before, what we do is we create this new list node, and let's say we're adding the data 4 into this. After that, we have our tail that is pointing to the last part of data inside of this linked list. If we take the tail.link and have it point to the new list node, and then update tail is equal to tail.link, we've sufficiently added this new element to the end of our queue. Let's see how this works. Public void enqueue, TA data. The first thing that we do is we create an instance of that structure. List node, new node is equal to new list node, a data. That way the data that we're trying to add is assigned. And also this is always going to be at the end of our linked list, so our link should be null. Now, whether we're adding or we are removing, there's usually a case that involves the first element. So if we have an empty list, we have to make sure that the head reference points to the first element in this list. So if head is currently null, so this is an empty list, what we need to do is assign head and also go ahead and assign tail to the memory address that's stored inside of that new node. And once that's finished, we return. Now, if the list is not empty, that means we need to take the tail, which is currently the last element in this linked list. If we assign its link, which is currently null, it's pointing to nothing, but now we have it point to the memory address at this new node. Well, now we've added that last element to the end of this linked list. After that, if we advance tail is equal to tail.link, now we have finished enqueuing this data. Whenever we were looking at this in a generic linked list, we had to find that last reference. However, could you update the generic linked list to now have a tail reference and basically do the same thing here for that add method? You absolutely can. These are your data structures to create and modify how you see fit. And if you see fit to have a tail reference in your generic linked list, then write it. Now let's see how dequeue works in a linked list based implementation of a queue. Dequeuing works much in the same way. The first thing we do is save a reference to the data that's stored in the head, move the head forward, and then return the saved reference. So starting for right here, we have a return value that we just assigned to the data that's stored in the head. Then we advance the head forward. Now, as there is no way for us to reach this node any longer, we can assume that a garbage collecting language like Java will go along and free up that memory, thus deleting it. Now let's see how that works in code. Going over here, public T dequeue. We remove and we return when we dequeue. First thing, if head is equal to null, so we have an empty list, we need to return nothing. Now, if that is not true, then what we need to do is save this return value is equal to head.data. Save the reference to the data that we're about to return. Then we update head is equal to head.link, advancing the head forward, and then return ret. And that's it. A lot of this code becomes simpler only because of that initial rule. Queues are first in, first out data structures. You only enqueue specifically at the end of the queue, and you only dequeue specifically from the head of the queue. Now the last two methods we need to create are peek and print. Public T peek. Now this observes the first element but doesn't remove it. So once again, if head is equal to null, so this is an empty list, well, we're going to return nothing. But otherwise, we're going to return head.data. Now let's do print. Public void print. Now doing this in a slightly different way, we're going to do a for list node temp points to the head, while temp is not equal to null, temp equals temp.link. Then after that, system.out.println temp.data. And now we've created this linked list implementation of a queue. Let's see how this works. Now going over to our tester, we have constructed this queue as an array queue. But now, as we have this linked list queue, which implements this queue, and this array queue that also implements this queue, what I can do is adjust this. Watch. I'm going to now create this as a linked list queue. I changed one statement, and now I have a completely different implementation of a queue that works in the exact same way. Running this, sure enough, nothing changes here. However, the entire back end did. This was originally an array queue that I now updated to be a linked list queue. Now, this is the power of polymorphism. You have one concept that is implemented in vastly different ways. This gives you a great deal of flexibility when you're writing code, and being able to recognize when one thing can be implemented in multiple different ways, and using polymorphism to use that can make you a really great programmer. Now, this lecture has been focused on this new data structure called a queue. The main idea of a queue is it is a first in, first out data structure. You process information one at a time, first in, first out. You can implement this using an array or using a linked list. In the next couple of classes, we're going to be exploring other types of data structures that also have similar kind of rules. And with all that being said, I'll see you next time.